Hello. So it's Dr. Daystorms, and this week, since the building is under construction, we have to do our organic lectures utilizing videos. And so this chapter 12 of your book, really is a continuation of chapter 11. And I mean, it literally picks up right where we left off. And from last chapter, we were talking about the two different types of broad general classes of reactions that involve benzene. Remember what benzene looks like, and the fact that it's an aromatic compound. Okay. And one reaction involving benzene, and the one that we went over, one class of reactions that we went over last time, was how the ring affects the reactivity of substituents hang off of the ring. Okay? So we have, remember, it made the benzylic carbon, let me change colors here. Like, if there was a carbon hanging off over here, it has a slightly more stable carbocation or carbon radical, free radical, than what you would expect. Okay. Alright. The second class of reactions, which is what this chapter primarily deals with, we're talking about the reactions involving the ring itself. So we're looking at reactions involving involving the ring itself. Okay, and there are two types of these reactions, just broadly. So this chapter has to do with reactions that occur on the ring. Alright, one is electrophilic aromatic substitution. So we have electrophilic, aromatic, because it's the ring, substitution. And then the second one is nucleophilic aromatic substitution, which doesn't occur as often because of the fact that the benzene ring is more stable than like a traditional alkene. Okay? And so the vast majority of this chapter deals with electrophilic aromatic substitution. Remember, an electrophile is something that loves to be attacked, right? It's something that goes, excuse me, sorry about that. It's something that can be attacked easily. So this is where the ring, we're going to find out, does the attacking. The ring behaves almost like the nucleophile to go and attack the aromatic. And then, and what it's in the substituting for hydrogen. And then nucleophilic substitution was where the ring gets attacked. And once again, we're talking about a specialized case there. Right up in the beginning, I want to tell you that there are three tables in this chapter. In table 12.1 and 12.3, these two tables really are the same thing. It's just 12.3 is more in depth than 12.1, but they are very important. Okay, 12.2 is a good barometer or a good guide to use, but 12.1 and 12.3 really are the crux of the chapter. So first, let's review electrophilic aromatic substitution from last semester. This is something that happens with alkenes in general. So we have our generic alkene here, and remember, you still have to remember Zaitsev's and Markovnikov's rule from last semester. Then we have whatever will be the electrophile that's being added to it, and I've just drawn a generic EY compound here. And in it, if you think back to last semester, we have an electrophile. Is it more or less electrophilic than whatever's attached to? It's actually less. Well, no, check that. I'm sorry. Is it more or less electronegative than whatever it's attached to? An electrophile is going to be less electronegative because it wants to love those electrons. So it's going to be delta plus, or it could even be, in an extreme case, something that's positively charged. Whatever it's attached to will be delta minus, so it's going to be whatever is more electronegative. Right? Let me erase these and get these out of the way. Now, as we go through these videos, feel free. You know how in class I usually stop and have you work something out? You may want to periodically pause the video as you're taking notes, try to work out the problem, and then come back and see how we do in the video. So you may want to pause it right now and just think back to what the reaction mechanism, because you need to know this mechanism here, what the reaction mechanism is for an alkene. And then come back and check to see if it works. I'm going to give you a moment to do that on your own. Okay, so let's work out this reaction mechanism. What do we have here that's more electronegative, has lone pair electrons, or at least is electron rich? What's electron rich is the double bond itself. So what happens is the electrons from the double bond is going to swing out and attack whatever's delta positive, which we already know is the E. So it swings out, boom. Sound effects optional. And then something has to break or give. And what happens are these two electrons go towards whatever is more electronegative, the EY. In doing this, we're going to end up with the following. I'll try to keep it color coordinated. Compound. And the way that I have it drawn here, once again, you have to follow Markovnikov's rule. Let's see. We have the E. We have the Y. And the Y here is going to be negatively charged. And we have the carbocation. So now what do we have that is going to be able to do the nucleophile and do the attacking? It's the Y portion and the EY. So what happens here now is that it goes and attacks the carbocation. Boom. So the resulting product would be as follows. We have the two original carbons, but now it's an alkane, not an alkene. And they're attached to, we have the electrophile on one, the Y on the other. So it's an electrophilic addition. It's not an electrophilic substitution. This is an electrophilic addition. So now let's look at what happens with respect to something that's an arene group, an aromatic, like benzene. So with benzene, we have these three alkene groups. However, remember this is an aromatic compound, so there's resonance through here. So it really looks more like that. So we don't have a single double bond, like just an individual double bond that can go out there and do the attacking per se. So we're not going to have an electrophilic addition in that sense. Instead, it's going to be an electrophilic substitution reaction, where the electrophile is actually going to be substituting for one of the hydrogens that's hanging off. Okay, so let's work this out. Erase everything. So in general here, I'm going to just draw it sort of the way that your book draws it. You have your aromatic. Let's go back. Let's draw it like our benzene ring. And I'll even draw where the resonance is occurring. And what it is we have a hydrogen. We have our EY group, which once again, the E, the E is delta positive, the Y is delta minus. The ultimate product here is going to be, once again, I'm going to try to, instead of being an addition reaction, it's a substitution reaction. So we still have the benzene ring. The benzene ring still has its resonance. That's the important thing, because remember, it adds to its stability since it's aromatic. But instead of the hydrogen, what's really cool about this is the fact that the electrophile has replaced. That's why it's a substitution reaction. This is an electrophilic aromatic substitution reaction. Now you are required to know this mechanism. Okay? So and what's really nice about this chapter is, for the most part, if you know the generic electrophilic aromatic substitution reaction mechanism, you know it for everything. Okay, so just learn and understand this generic mechanism, and you're good to go. Alright, so if we were on the board, I would put an asterisk by this. Okay, so this is the electrophilic aromatic substitution reaction. Once again, you need to know this mechanism. It's electrophilic because it's the electrophile that's going to be added to the benzene ring. It's not the nucleophile portion of the compound that does the reacting here. Okay, and to review, if we look at our generic, nucleophile, electrophile compound, which side of this is delta positive and which side is delta negative? The delta positive is the part that is less electronegative, so it's the E. That's the delta positive side. The delta negative side is by the Y. Okay, so let's now think about what do we have here that is electron rich that can do the attacking. One thing that's electron rich really is the Y portion, but that's already attached to the electrophile, so we can rule that out. The other thing that's electron rich is the benzene ring. Okay, now for clarity's sake, this is benzene, and so it's actually got 6 hydrogens hanging off of it, but I've only drawn one in for clarity so that it doesn't get too cluttered. We'll talk later on about what happens if there's more than one, if there are other substituents hanging off of it. But right now we're only looking at benzene. So the first thing that happens is one of the double bonds is going to swing out like a lever and attacks the delta positive E portion of the other compound. Boom. Sound effects optional. Now something has to break or give, or otherwise that E is going to have too many bonds around it. So the bond between the E and the Y breaks, just like what we've seen in the past. And the Y leaves. Okay, so let's now draw the compound, what this will look like. So far, this isn't anything different than what you'd expect with a normal alkene. Okay. We still have a hydrogen. Okay, but we have the electrophile is now covalently attached to the benzene ring, and we have a carbocation, which I will put in, I don't know, a slightly different color. Okay, now this carbocation is somewhat stabilized because there's resonance still possible in the benzene ring, but I'm not going to show that at this point because otherwise it would become too cluttered. And we also have the Y portion of the nucleophile, which I'm showing as a negative. Okay? So, now I want you to think about what do we have now. It's either delta minus or negative that can do the attacking, and what can be attacked. So I'll give you just a moment to think about that. Now, your first instinct will probably be that the nucleophile portion of the previous compound can do the attacking, and that's correct. It is negatively charged. your first inclination is probably to have it go and attack the carbocation. But if we do that, the resulting product will not be a benzene ring. So that's wrong. Instead, what's really interesting, or at least I think is cool, is this goes and it takes the hydrogen that is attached to the same carbon that the electrophile is attached to. But it just takes the proton portion. The two electrons here that's holding that hydrogen on actually stay, and instead what they do is they swing down, boom, to reform the benzene ring. So because of this, we're going to end up with this final product. We reform our benzene ring. Okay. And we now have, whoops, wrong color. Just a second. An electrophile attached in place of where that hydrogen was. That's why it's called a substitution reaction. We also have the nucleophile and portion of the original compound, and it has attached to it, or associated with it, because sometimes it's an acid, the hydrogen from the benzene. So we have successfully performed an electrophilic aromatic substitution. You may want to practice this mechanism on your own some before we go on to the next portion of this video. So, tables, once again, just to remind you, table 12.1 and 12.3 actually go over the different types of electrophilic aromatic substitution. So next, I'm going to actually just draw out a bunch of the compounds that we can use. The hardest part here is actually thinking about what portion of the compounds of your EY, what portion of it is the E, what portion of it is the Y. So for example, we can do what's called a nitration reaction. That's using nitric acid. We can do sulfonation, which sulfonation uses sulfuric acid. And the hardest part, once again, is trying to figure out what is the E and what is the Y of each compound. And then there are also different types of reaction conditions for each of these. Then we can do halogenation. Usually with halogenation, we're talking about bromine or chlorine. Those are the two that work the best. Right? Then we have the two Friedel-Crafts, and I'll write that out in just a moment, reactions. We have what's called Friedel-Crafts Alkylation. So that's where we are using an alkyl halide. And then we have Friedel-Crafts Acylation. And that's when we're using an actual acyl halide. Usually it's going to be an acyl chloride. Okay? Once again, these are each going to have their own reaction conditions, and you have to figure out which part of each of these compounds is the E, which part is the Y. So let's first look at the nitration reaction. So let's do this one first. What I strongly suggest that you do is draw the Lewis structure. So I'm going to draw it in large over here in this color, what it looks like. Okay, and if you put in the charges for each of these, we're going to have a negative charge on this oxygen and a positive charge on the nitrogen. Alright, so now we have to think about which part of this is the E and which part of it is the Y. Now, your gut instinct may very well be sorry about that. that the E portion is all of this, and the Y portion is that oxygen. That's not quite right, and the reason why is because the reaction conditions that we do nitration reactions in, this is the reaction condition. And so, let me see. You have to take your, I'm just going to use it, it's an air ring group like your benzene, and it's going to be nitric acid. But you have to do it in the presence of sulfuric acid. What happens is the sulfuric acid reacts with the nitric acid in order to make this portion much more electrophilic. Much more nucleophilic than the nitrosyl group. Okay, so that the the OH becomes more delta minus, and so that is your Y, and this becomes your E. Okay? We're going to work through more examples, but once again, we can probably see, you can tell the nitrogen itself is, it's positively charged. The oxygens are going to be delta minus, but the OH group is a much better leaving group. And so your final products will be the nitrosyl group goes on the benzene, and we get water because you get HOH. Okay, so let me erase that, and we'll go through and we'll do another example. Okay, so now in this time, let's work on doing what's called sulfonation. Sulfonation uses sulfuric acid, and the only reaction condition for it is heat. So to do nitration, you do not add heat, because the nitration reaction requires nitric acid in the presence of sulfuric acid. If you add a lot of heat to it, it'll do sulfonation instead. Okay, so let's draw, the easiest way is draw out what sulfuric acid looks like. And then just think about what portion of sulfuric acid, here, let me erase this one part, because I didn't do a very good job drawing it. What portion of sulfuric acid is delta plus, and what portion of sulfuric acid is delta minus? So just think about it for a moment. Okay, the delta plus portion, I'm going to use a different color, which is more electronegative, a sulfur or the oxygen? Oxygen is more electronegative, that's correct. So what we're going to do here is that means that the sulfur is delta plus, the oxygen is delta minus. So that means that this portion right here is going to be your Y. Everything else will be the E that gets added on. So you're going to add on the sulfonyl group. The mechanism is the same. Okay, we'll do one or two of these examples later on. Right? So now let's do bromine or chlorine. So if you look at the, I'm going to do bromine, but the same, you could do chlorine instead. But if you look at the Lewis structure for it, and you don't overthink it, you know, which section of this is more electronegative, one bromine or the other? And the answer is they're the same. And so it really doesn't matter here which one is the E and which one's the Y, because they're identical. So you're going to be adding a bromine on instead. Now, the important thing here is the reaction conditions. When you normally do it with other alkenes or alkanes, remember we added in heat and light because it's a free radical. But if you're doing this with bromine or chlorine with a benzene ring, this is what it's going to look like. You know, I'm going to do bromine, but you could do the same thing with chlorine. The reaction conditions here, you have to have a special type of catalyst. And the catalyst is iron 3 bromide. if you're doing chlorine, it would be iron 3 chloride. And if you do that, you're ultimately going to end up with bromobenzene or chlorobenzene. So remember, it is not heat and light. That is for other alkanes and alkenes. Okay, so that's a big no-no. If you see that, you would actually halogenate the functional groups hanging off of the benzene ring over that of the actual benzene ring. You must have either iron 3 bromide or iron 3 chloride. Okay, the next class of electrophilic aromatic substitution reactions is called the Friedel-Crafts Alkylation. And so this should already give you an idea of what's going to be going on. Alkylation means we're adding an alkyl group, so a carbon-containing group. Okay, and so we start off with an alkyl halide and benzene ring, and this one does require a special type of catalyst. Okay, the type of catalyst that it requires is called the Friedel-Crafts. It reacts with the Friedel-Crafts catalyst, and usually this is done at lower temperatures. Okay, the Friedel-Crafts catalyst is aluminum trichloride. I guess in theory aluminum tribromide would also work, but aluminum trichloride. Once again, we're usually talking about very low temperatures. Now, if we just look at the Rx, which one's delta plus and which one's delta minus between a carbon and a halogen? Oh, I've actually already got that. Well, it's fairly simple. The carbon is going to be delta plus, the X is going to be delta minus. The way that this works, and the reason why we have to use the Friedel-Crafts reagent, is when you look at aluminum trichloride, what's really cool about it is aluminum actually can take a fourth substituent, and so it adds that X. It adds that X to where now what you can get instead is that this behaves much more, instead of looking and behaving like an alkyl halide, it looks and it behaves, here, let me make some more room, like this, where the aluminum takes on a negative charge and it's coordinated to that R group, which is more, so it acts like it's a carbocation. So that's why it makes it really easy to tell which part of this is the E and which part of this is Y. This is the E, that's the Y, is really that X group that had been there. Okay? And so what you're going to end up getting, and it's only transitory, you get your aluminum trichloride back, and so your final products here would be the benzene ring with whatever your X was, with whatever your R group was, plus HX. Okay? So next up is Friedel-Crafts acylation. And if we just look at the acyl halide, which part down here is delta plus and which part's delta minus? Well, between the carbon and the chlorine and the carbon and the oxygen, the carbon is going to be delta plus. The chlorine is delta minus. Okay, so all of this is the E, that is the Y. But similar to the Friedel-Crafts alkylation, this has a different, it's at relatively low temperatures, and once again you have to use the Friedel-Crafts catalyst of aluminum trichloride. It makes the acyl group act as if it's a carbocation, and what you end up getting for your final products, I'm going to actually draw it above, is now we have a benzene ring with an acyl group attached to it plus HCl. Or HBr if you start with an acyl bromide instead of an acyl halide. We're going to find out the reasons why, how this comes in, and how this is important later. So let's look at some examples. In this first example, the one at the top, we have benzene ring and bromine. And if we want to do bromination, what catalyst do we have to use? Remember, it can't be heat and light. It would actually be iron 3 bromide. It's supposed to be Br. And we would end up with the benzene ring with the bromine hanging off of it plus HBr. Now, we have here, and you haven't learned how to name this one, but this is butanoyl chloride. But this is a Friedel-Crafts Alkylation. So what part of this is the E and what part is the Y? This is the E, that's the Y. Okay, so the final products would be our benzene ring, carbonyl 1, 2, 3, 4 carbons hanging off of it, plus HCl, which is an inorganic product. And finally, we have nitration. The reaction conditions to add a nitrosyl group to it is sulfuric acid, but you do not add heat. It's going to be at low temperatures because otherwise they'll do sulfonation. Because sulfonation is easier to do than nitration. And we're going to end up with an NO2 group hanging off of it plus water. Because it was an OH that left the nitric acid. Just practice doing more and more of these, and it should come more second nature. In the next video, we're going to actually talk about what happens if there are things hanging off of the benzene ring besides hydrogens, and how that affects the location and the reactivity of the substitution reactions. And I will hopefully post the video within the next couple of days at the latest, and that we'll also have our quiz this week that's going to be available online, and I'll send out an email once it's available. See you in class later. Bye.